All right. Exponential function. Let a and b be real number constants. An exponential function in x is a function that can be written in this form. I am assuming you guys have seen this before in Algebra 2. Exponential functions and logs. You guys have seen that before? Okay, wonderful. We're going to do even more with it. So this is just a quick overview, a quick review of the basics. This is, of course, where a is non-zero, b is positive, and b does not equal 1. The constant a is the initial value of f, the value at x equals 0, and b is the base. And then we're skipping growth and decay, going down to logistic population model. So this is where you have an exponential growth function that has a limit. Like there's some limit where your exponential growth does not pass. So what will happen is, with an exponential model, with an exponential model, it'll look like this. Whereas with a logistic model, it'll look something like this. There'll be some asymptote up here that it doesn't cross. So it's a different function. It's either this or this, depending on if the base is e or if the base is some other constant. So exponential growth is unrestricted, but population growth is often not. For many populations, the growth begins exponentially, but eventually slows and approaches a limit to growth called the logistic growth function. Let a, b, c, and k be the constants, with b less than 1. A logistic growth function in x is a function that can be written in this form, or this form, where the constant c is the limit to growth. If b is greater than 1, or k less than 0, these formulas yield logistic decay functions unless otherwise stated. All logistic functions in this text will be growth functions. Generally, we're only going to deal with growth functions. We're not going to deal with things declining. Yes? Yes. In short, you just need the basic function. I do want to get you guys to get used to the way these things are worded, because it can be a little overwhelming if you're not accustomed to reading this stuff. Anyone need more time to copy this? All right. Okay, example number 1. For each model, P represents population of the city proper and T time and years since 2010. Tell whether the population model of each city is exponential growth or, hold on one second. I think I may have cut that part. Exponential growth or decay. Does everyone know how to determine if something is growing or decaying? Okay, good. Exponential growth or decay, find the growth or decay factor and the constant percentage rate. Okay, so, let me do this. Let's do this. Let's focus on A. Graph this and tell me if it's a growth or a decay function. Or if you can just look at it and tell if it's going up or going down, great. And put it on your whiteboard and I'll give you a point. So you can just put growth or decay. Basically, you're determining is it going up or going down from left to right. You can graph it, but hopefully you can also kind of see. You guys know what an exponential function looks like? You can determine if there's any kind of reflection going on. In this case, there isn't. Okay. One, you guys got it? Everyone got it. It is a growth function. Can you guys figure out what B is? From f of x equals a times b to the x power. Can you guys all figure out what B is? No, for San Antonio. So the first step was, is it growth or decay? It is growth. So figure out what b is. So the function is f of x equals a times b to the x power. B is the common ratio. What is b? Okay. That's correct. It's one of the numbers given. Yeah. Okay, that's correct. Yes. So looking at the equation, what is all right, awesome job, you guys. Okay, looking at constant percent. Okay, looking at the constant percentage rate. So, a good way to demonstrate this, if you went shop and let's say there was this shirt that you wanted to buy, and let's imagine that one day you went to the store and the shirt price had increased by 20%. What you would do is you would take the original price of the shirt and multiply it by 1.2. And that would give you the 20% increase. Did that make sense? Now, in reverse, if you were given something like this, and they said, what is the percent increase? You could look at this and go, oh, well, 1.2 minus 1, it's a 20% increase. We have determined that this is an increase, and you determine that B is 1.0168. Can you determine the percent increase based on that? Give me the percent increase based on that. And as always, once you get it right, just check in with your teammates, make sure everyone's okay. Yeah, actually, give it to me as a percent. That's right. Too many points. Too many. Just two to the right. Yes. Good job. Yes. Got it. All right, everyone got it? Great job. Here is the answer. Are there any questions? All right. Any questions on this? Does anyone need a little more time to copy it down? All good? Okay. So turning the page, we have Detroit, Michigan. Can you guys give me B and then also tell me if it's growth or decay? Give me B and also tell me if it's growth or decay. I'll give you 1 point for each.
correct. 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 Yes, everyone got it? All right, here is B, and yes, it is a decay function. Please give me the constant percent decrease. So same idea, except now we're measuring what percent is it decreasing? I think you moved the decimal one too many places over. Yep. You're good. Yep. You guys are awesome. Here, I thought this would be hard. All right, here is the answer. So because it's decreased, we are subtracting from 1. We get this. Written as a percent, it's 0.7% decrease per year. Any questions on B? All right, let me see how to do this. Take a look at example number 2. Do you guys feel like you can solve those? Or would you like an example or two first? Example or two first? Okay. How about I'll do A and B as an example, and then I'll let you guys do C, D, and E. Does anyone need a little bit more time to copy this down? I see people writing hurriedly. I will wait a second. Anyone need a little bit more time? All right. Okay, so example number 2. Which of the following are exponential functions? For exponential functions, identify the initial value and the base. That's A and B. If not an exponential function, explain why not. All right, so f of x equals 3 to the x power. In this case, the initial value is 1 and the base is 3. So in the formula, a times b to the x power. To get this, you have 1 times 3 to the x power. Does that make sense? It is an exponential function because we have a variable as an exponent. Yes. Well, what would the initial value be? So when x is 0, what is the value of the function? It's 1. All right, now for b, this is not an exponential function because the exponent is a -4. There isn't a variable in the exponent. This is a quartic function, I guess. Just a polynomial. Yes? If you have an x raised to an x power, we're not really going to be looking at functions like that in this class. I actually don't know what that would be yet. I think that's a different, completely uncategorized function. Yeah. Yes? Yeah, so you see how there's a variable in the exponent here? This one does not have a variable in the exponent. The exponent is a -4. So it's actually a rational function now that I think about it. Sorry, I said a quartic function, but that's not correct. It would be 3 over x to the 4th power. All right, take a look at C, D, and E. Do you guys feel like you can do those? Yeah? Okay, please do C, D, and E. I'm trying to cover up the answers. So for each of these, you're going to tell me the initial value on the base, or you're going to tell me why it's not an exponential function. Go ahead. I'll give you 1 point for each one. So remember, in order to be an exponential function, it has to have a variable in the exponent. Okay? All correct.
Good job.
Oh, sorry.
Wait, are you writing yes or no?
All correct. So you're telling me the initial value on the base, or why is it not a function, or why is it not an exponential function? Yes. Tell me why. Why is it not exponential? Yes. Good job. All right, everyone got it? Here are the answers. So e is not an exponential function because pi is a constant, so this whole thing is just a number. There's no variable at all. And the rest of these are exponential functions. All right. Are you guys all familiar with natural log and e? You guys learn logs, right? Yeah? Okay. So natural log and e, you know that natural log is log base e. Okay. Does anyone need a little bit more time to copy this down? All right. So the natural base, e, since f of x equals e to the x power has special calculus properties that simplify many calculations, e is the natural base of exponential functions for calculus purposes, and f of x equals e to the x is considered the natural exponential function. Here is the definition. We are not going to be doing anything with this definition. All you need to know is that e is a number that's going to become very special to you when you get to calculus. It's kind of like the pi of upper level math. You use it for a lot of stuff. Okay? For now, this is the number that it equals. In this class, you just need to know that natural log is log base e, and it is very commonly used in logarithms. Exponential functions and the base e. Any exponential function f of x equals a times b to the x can be written like this if you needed to. So if you had something like this and you needed to convert it to a base of e, you can do that. You just need to figure out what coefficient to put on x in order to make that happen. For approximately chosen real number, constant k, and this is all the same stuff as regular exponential functions. I just realized your back is completely towards me. Did you guys want to pivot the desk so that you don't have to? It's up to you. Okay. You could even just swivel your desk over so you don't have to. Yeah, it's supposed to be like the crisscross is supposed to point to the TV, but it always gets messed up, so feel free to move the desk however you need to. Alright, would anyone object if I just went over the last example and the exit ticket? Did anyone have their hearts set on doing it as a team for points? Okay. Alright, so example number 3, we get into graphing exponential functions. So what I've done here, as best as I can, the blue graph is e to the x power, and then the pink graph is the transformed graph. Oops. Forget this part. Just use dilation. There you go. Excuse me. Okay, so this is this is e to the x. Horizontal dilation by a factor of 1/2. It looks something kind of like that. And I'll graph it on my calculator too so you can see it. Is everyone able to find E on your calculator? It's the blue thing above the division symbol. Okay, so e to the x, e to the 2x. There's e to the x. There's e to the 2x. This is something kind of like that. E to the negative x, it's a reflection across the y-axis. So there's e to the x, and there's e to the negative x. Something like that. And finally, if you multiply by 3, it's a vertical stretch or a vertical dilation. Looks something like that. Notice that this is the only one where the y-intercept changes. On both of these, the y-intercept stays the same. But when you have a stretch, a vertical stretch specifically, the y-intercept will change. Did I go too fast through that? A little bit? Do I need to go back at all? Farther? So here's B. Do I need to go back to A? You got it. Here's A. Back to C. More time. More time. I'm going to go back to C. Is that okay? Okay. All right, here's C. And again, I also encourage you to graph these on your calculator so that you can see it. All right. So the exit ticket is meant to be a review of the basic graphs. Ideally, you would solve this without a calculator. Can I turn the page? Does anyone need a few more seconds? It's okay if you do. Just let me know. So what they want you to do here is they want you to graph each function and give the end behavior. So in each case, the end behavior is either going to be infinity, negative infinity. I think there's one where the limit doesn't exist. So here, the limit as x approaches infinity is infinity. The limit as x approaches negative infinity is negative infinity. This one, both sides are going up. So it's positive infinity, positive infinity. Notice that with end behavior, you're always looking at where x approaches infinity and where x approaches negative infinity. Same thing for x squared. It's going up and up. Infinity and infinity. X cubed looks like this. So it's going up this way, but down this way. So we have infinity and negative infinity. And finally, the square root of x looks like this. So as x approaches infinity, that equals infinity. But the graph of f of x does not approach negative infinity. So that limit does not exist. Okay. You guys did awesome. Thanks so much. I can go back and forth if you need to copy this down, but I'm hoping you guys could figure these out on your own. To get ourselves a piece. Inspire us to act justly to revere all God has made. With peace firmly in our hearts and in the world. Amen.